Hey, we're going to do our last bit of trig here, and we're going to talk about angles of elevation and depression, which is mostly the same kind of thing that we've been doing, but with a little bit of vocabulary. So here I have a fun little cartoon to sort of illustrate what angles of elevation and depression are. So if I have this goofy little airplane up in the sky and this goofy little boat in the water, if you're up in the airplane and you're looking down along this sort of pink line down towards the boat, and then you look straight out, straight ahead, these two sight lines create what we call an angle of depression. So the angle between the plane somebody on the plane looking straight, horizontal, and then looking down towards the boat is this angle right here, and we call that an angle of depression. It's an angle that's formed by looking down. If you're in the boat and you look up at the plane, we have an angle of elevation. So this angle is formed by looking up and looking out, straight ahead. You might notice that these two green lines are parallel, which makes the pink line or purple line a transversal, and these two angles, this depression and this elevation angle, are alternate interior angles. They're equal to each other. So if I know the measure of this angle of depression from the plane to the boat, the angle of elevation from the boat to the plane is going to be the same. And the way that this ties into trig is that these pictures can be sort of completed here, and we have two right triangles. So we can use some trig, some angles of depression or elevation to figure out distances, and that's what we're going to do here. So we have a sort of a dreaded word problem here, and we're going to have to draw a picture in order to figure out an answer. So we have this person flying a kite, and you might be an artist, so you can get creative if you want to. I'm not an artist, so I'll draw a stick figure. She's flying this kite up in the sky, and my string is 200 meters long. And it says when Susie looks up to her kite, there's an angle of elevation of 38 degrees. That angle is formed between Susie looking straight and her looking up. So this is my angle of elevation of 38 degrees. We want to know how high off the ground the kite is. Well, if we finish here and create this right triangle, this distance here is going to be how high the kite is. It's going to be off by a little bit because we don't know how tall Susie is, but we'll just take that into account as an error. So now I can just look at this as sort of a regular right triangle problem. X is opposite from my 38 degree angle of elevation. 200 meters represents my hypotenuse. So this is a sine problem. To get x, I multiply 200 on both sides, so I end up with 200 times the sine of 38. And if you plug that into your calculator, you'll get that the kite is close to 123.1 meters above the ground. So really sort of the added thing here on top of what we've been doing the last couple of classes is that we have to understand what it is to be an angle of elevation or depression, and we have to draw a picture. Then we can do some trigonometry. So we'll do another example. I have this guy sitting in a tree. Again, I'm not an artist. I'm not going to grade you on your picture, but it helps to draw one. So here's this guy up in the tree. He's looking down to this dog and it creates an angle of depression. So the depression is the angle formed between what it would, a straight horizontal line, and then looking down to this dog. I don't know. There's my dog. The tree is 50 feet high. And I have over here sort of the makings of a right triangle. I can finish that off. If the tree is 50 feet high, that means that this measure in the right triangle is 50 feet. Oh, I'm sorry, I misspoke. Hopefully you caught that. I said the dog is 50 feet away, not 50 feet high. So actually this distance, the dog is 50 feet from the tree, which makes this part of my triangle 50 feet. I apologize for that. We are looking for this side because we want to know how far Bobby would fall if the tree branch he was sitting on broke. So over here is my X. So X is my opposite side. This 50 feet is my adjacent side. That's going to tell me I should use tangent. I can multiply both sides by 50. Pop that in my calculator and figure out that if the tree ends up breaking, that Bobby will fall about 23.3 feet before he gets to the ground, which probably won't be a good thing. So go ahead and pause here, do your best to draw a picture, and figure out how far this ball has to travel. So I've got this guy, Schmearnest. And Schmearnest is a basketball player. So we can, try and draw a little basketball hoop. Again, doesn't have to be pretty, but you can have fun with it if you like that. And we see that he is 15 feet away from the basketball hoop. And he's going to shoot a brick. So for those of you who don't follow basketball, a brick means it's a bad shot, basically. And it's going to form an angle of elevation of 17 degrees. So that means this angle right here is 17 degrees. And so we want to know how far the ball will travel before it hits the rim, doesn't go in, and Schmearnest doesn't get any points. So that would actually be the hypotenuse distance. So we have the hypotenuse as x. We have this is our adjacent side, we know is 15. So we're going to use cosine here. So the cosine of my angle of 17 is the adjacent over the hypotenuse. We got to multiply both sides by x, which leaves us with x cosine 17 equals 15. Then we'll divide both sides by cosine of 15, which gives us x equals 15 divided by cosine of 17. And now we can just put that straight in the calculator and figure out that this ball is going to travel 15.7 approximately feet before it hits the rim, doesn't go in, and hopefully we don't lose the game there. So I've got one for you to try. You should draw a picture, you should show all your work in your notes, and then submit to me your answer, how far this airplane is going to travel horizontally.